So I was anticipating that I would come in today and there would be questions, perhaps over homework.
Yeah.
I was hoping there would be because there probably should be some questions. So, yes.
Number 5.
Number 5.
This is the trig.
Sine x, cosine x. All right.
Maybe super easy, but
All right, well, let's go through it, all right, because I didn't do any trig ones. We've got the function is f of x equals sine x plus cosine x. And they give you an interval 0 to 2 pi. Now, recognize that in the problem they are giving you a continuous function on a closed interval. But they're not asking you for the absolute maximum and minimum. They're asking you to figure out where it's going up, where it's going down, where it's concave up, concave down, inflection points, all that stuff, right? So even though we have a closed interval method for finding the highest and lowest points of this graph, that's not what they're asking for. All right, so what we did last time, we kind of went through this systematic sort of approach, right? We needed both the first and second derivatives. So those should be pretty clean, right? First derivative is cosine x, what? Minus sine x. And then the second derivative is negative sine x minus cosine x. So those are our derivatives that we'll be working with throughout the rest of the problem. So to figure out where my function's going up and where it's going down, I'm going to have to figure out where the first derivative is what? 0 and undefined if possible. Put those numbers on a number line, test some points, right? But I'm only going to be looking here, right? So first of all, when is the first derivative equal to 0? When does the first derivative not exist? Undefined. What about this one? Undefined. You want to finish up with that one right now?
yeah.
That's not going to happen, right? Okay, so don't have to worry about that. So I'm going to set the first derivative equal to 0. And then the question becomes, how do you want to solve that? There's multiple ways to solve it. What I would do is I would move the sine x to the other side to make it a positive. That's what I would do. And then I would just ask myself, where are cosine and sine the same? Right? Where are they equal? So if I go to my unit circle, remember that the points on the unit circle are the cosine and the sine. So where's the x value equivalent to the y value? Right here, right? Because they're both root 2 over 2, root 2 over 2. And down here, because they're both negative root 2 over 2, negative root 2 over 2. Those are the only two places between 0 and 2 pi where that happens. So the two solutions are pi over 4 and what's this one? That's this one. 5 pi over 4. You can count your way around. This is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. All right. Now, let's see, I'm recording, yes. Now what I'll do is I'll draw a number line. And I'm going to remember that I am only looking between 0 and 2 pi. And I'm going to plot these on here. We just need basically a rough estimate of where these are. Pi over 4 is here. And 5 pi over 4 should be here. So remember, these are the critical numbers, right? Those are the critical numbers. So I need some test points. So my test points are any point to the left of pi over 4, but it's got to be in this interval too. So what? Something in here? What? I did. Yeah, we could do 0. We could do 0. Y'all want to do 0?
Yeah.
Okay. We'll do 0. And then pi. And 2 pi. That's fine. The thing is, you wouldn't want to go outside of these, and the reason why is because we only looked for solutions to this between 0 and 2 pi. If you go too far out, you might actually be back to one of these solutions. So that's the danger in that. But we're OK with those. So these are test points, right? I want to test these. All those get tested. And when we say tested, what do I mean?
Put them in derivative.
Put them into the derivative.
First.
Yep. So what I want to now know is what is f prime of 0? What's f prime of 0? What's f prime of pi? What's f prime of 2 pi? And the derivative was cosine x minus sine x, right? So this is going to be cosine 0 minus sine 0. Cosine of 0 is 1. Sine of 0 is 0, so this is 1. All I care about is the fact that it's what? Positive. Cosine of pi minus sine of pi. So cosine of pi is what? Negative 1 minus sine of pi is 0. So this is negative 1, so that's a negative number. And then cosine 2 pi minus sine 2 pi, which is 1. So when I come back over here, I take a look at this. I know that in this region right here, my derivative was positive, right? My derivative over here was greater than 0, which tells me the original function f is doing what there? Increasing. Right? And then between pi over 4 and 5 pi over 4, my derivative was negative, which means my original function is decreasing. And then finally, in the last region, derivative was positive, which means my original function is increasing. So let's answer the question now for part A, because that's what they asked. For part A, where's it going up, where's it going down? So my function is increasing where? 0 pi over 4? Union? 5 pi over 4 to 2 pi. Where is it decreasing? Pi over 4 to 5 pi over 4. Part B, were there any questions? Part B is asking where do we have a local maximum, where do we have a local minimum? So part B, we have local max. Do we have a local max? Where is it happening? Pi over 4, right? At pi over 4. This is happening at x equals pi over 4, which means we would have to plug pi over 4 into the function to figure out what the maximum was, right? Into the original function. And that means I need sine of pi over 4 plus cosine pi over 4, which we already know sine of pi over 4 is root 2 over 2 plus root 2 over 2. What's root 2 over 2 plus root 2 over 2? It's 2 root 2 over 2's, right? It's 2 root 2 over 2's, which is just root 2. So my local maximum should be happening at pi over 4. The value of the function there is root 2. It's not, I'm not saying this is the absolute maximum. I'm saying it's a local max. I have a little hump there. It might be the highest on the entire thing. It may not. And how about a local minimum? Yes? 5 pi over 4? So for part B, we have a local minimum at x equals 5 pi over 4. And f of 5 pi over 4, if you do that, it's negative root 2 over 2 plus negative root 2 over 2, which is negative root 2. So same idea. You're plugging 5 pi over 4 into sine and then into cosine. Both of them spit out negative root 2 over 2. You put them together, you get negative root 2. We good? All right, we also need to figure out where the function is concave up and concave down. So now we're going to do the same exact process with the second derivative. So let's take a look at the second derivative, which I erased. But I can it's negative sine x minus cosine x. And so I want to know where the second derivative is 0 and where the second derivative is undefined. How about the undefined? Not going to happen, right? Nice trig functions there. So let's set it equal to 0. And how do you want to go about solving that?
Take the negative.
You want to take the negative out?
Take a negative 1 out.
Out of the whole thing?
Yeah.
You can do that. And what do you want me to do?
Let the both equal to 0 again and move it over.
That's a legal move. How about dividing both sides by negative 1? Then it would be this, right? Nope, because it's not multiplication. It's addition. What did I do on the last one? I moved 1 over, right? If you move 1 over, you might be able to see this. Sine x equals negative cosine x. What is this saying? It's a little different than the one before. It's not where they're equal, it's where they're what? Where they're off by a sign. So where on the unit circle are your x and y coordinates? Because that's sine and cosine. Where are they the same, but they're different in sign only? Right here and here, right? The coordinates of this point are negative root 2 over 2, root 2 over 2. The coordinates here are root 2 over 2, negative root 2 over 2. And so they're almost the same, right? They're just off by a sign. That's what this is saying. They're the same, but they differ by a sign. You understand that? The equality of these, the sine and the cosine are identical, off by a sign. So 3 pi over 4 and 7 pi over 4. So from that, I have a new number line. Here's 0. Here's 2 pi. Here's halfway, halfway, halfway. Quarter, 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 quarter. So 3 pi over 4 is here. 7 pi over 4 is here. And so I need some test points. You want to do 0, pi. So same ones, 2 pi. But this time they're going into the second derivative instead of the first derivative. So what's the second derivative at 0, second derivative at pi, second derivative at 2 pi? Here's your second derivative. So we have negative sine of 0 minus cosine of 0. What do we get there? Negative 1, which means it's a negative number. Okay? And then when we do negative sine of pi minus cosine of pi, we get what? We get positive 1, right? Sine of pi is 0, so that's all gone. Cosine of pi is negative 1, but then minus, so 1 here. And then we do 2 pi, we should get negative 1 again. Questions on that? Had you gotten like to this point, or were you, no?
I was stuck at the, pretty much the beginning.
Okay,
I didn't have like,
okay. Is this making sense?
Oh, yeah.
All right. So we take this information, we know that over here, right, my second derivative is negative, which means the original function is what? Concave down, right, like this. And then here at pi, it's positive. Second derivative is positive, which means the original function is concave up. And then this last little region here, the second derivative is negative again, which means over here I'm concave down. And now we'll summarize this with some intervals. So answering part C. F is concave. Let's do up first. Where? 3 pi over 4. 7 pi over 4. And F is concave down. 0 to 3 pi over 4. Union 7 pi over 4 to 2 pi. Yes. Yeah, to 2 pi, because we're stopping it. Yes?
So does that mean there's two inflections?
That's exactly right. We have 2 inflection points. That's the next thing we need. Inflection points. I'll put point slash points, because you can have more than one. In this case, we have more than one. So where are our inflection points? At 3 pi over 4 and 7 pi over 4, because that's where we change from concave down to concave up, and then concave up to concave down. So anytime you switch, that happens, yes.
On the test, because I know in the book they're asking for the inflection points like with the y-axis too.
With the y-coordinate?
Yeah, with the y-coordinate. I mean, I know you just plug it in with the here for the test. Do you want to just show where it's going to be?
Yeah, because yes, you'll have to figure out what the y-coordinate is. Yeah.
And you plug that into the original.
To the original function. Yep. So this is where the inflection points are happening, here and here, right? Inflection points are at those x values. And so if we want to know where they are in the graph, we have to plug those into the original function. See, it's not a max min, so it's not like we're trying to find but you could still do it. Let's do it. What's f of 3 pi over 4? So that's sine of 3 pi over 4 plus cosine of 3 pi over 4. Hey, wait a minute. It should be 0. Right? Sine of 3 pi over 4 is root 2 over 2. Cosine of 3 pi over 4 is negative root 2 over 2. And so these become 0. And the other one is 0 also. Now, I want you to see something. This is leading into what we're doing today, okay? I mean, we're done, right? We've answered all the questions? Yeah? Any questions? Sure? Okay. So this is going to lead into what we're going to do today. I want you to watch something. Because we've gone through all that work, so I want to make it worth our while here. What I'm going to do now is I'm going to put some information up here and see if you can follow me on this. And try and leave yourself some space, all right? Like this is going to take up like maybe half a page, all right? So across the top, I want you to draw a number line. I want you to go 0 to 2 pi. And leave some space above this also. I mean, enough for a couple of lines above this. Don't make this at the very, very top of your page. What were the critical points what were the points where our first derivative was 0? Where was our first derivative 0?
X equals 9.
Yes, what did we get?
Pi over 4.
Pi over 4. So I'm going to cut these into quarters here. That was right here, right? Pi over 4? Yes?
Yes.
Okay, so what I'm going to do is I'm going to draw a line straight up from there. All right, our other one was where? 5 pi over 4? Like this. All right. That was from the first derivative, right? Now, from the second derivative, what were those points that we had that were important? 3 pi over 4, which was here, and 7 pi over 4, which was here. Y'all all right with this? Now, up here, I would like for you to draw a line across, and I want you to make 2 lines which will create 3 rows, right? I've created 3 rows by drawing 2 lines. And then on the left-hand side here, I want you to write next to this row off to the side, I want you to put F prime. On the row above it, F double prime. and the row above that, f. Now let's talk about f prime. Go back to the picture we had, because we drew something for f prime, didn't we? And I showed you where f was going up and down and all that stuff? Yes? So where was f prime positive? Where was the original function going up and down? Or tell me from left to right what it did. It was up until when? Pi over 4. So if I drew an arrow right here, would you agree that's what the function is doing there? And then it goes where it starts going down right here? And it goes down until I get to where? 5 pi over 4. So is it safe for me to put this down arrow in there also? And then from 5 pi over 4 to 7 pi over 4, is it down or up? It's up. How about from 7 pi over 4 to 2 pi? Still up? Do y'all see what I've done? I've used the information from my first derivative to figure out what's happening in each of those little boxes. Now let's do the same thing for the second derivative. What was the second derivative doing? What was it telling us between 0 and pi over 4? Were we concave up or down? Down. We were concave down here? We were concave down until I get to where? 3 pi over 4. So would you say here is also down? And then 3 pi over 4, that's where I switched to concave up? Until I get to where? 7 pi over 4. So that's this and that's this? Yeah? Once I get to 7 pi over 4, from 7 pi over 4 to 2 pi, it went back to concave down? Okay. Everyone see this? No questions? Now we have to think about this. And I'm going to put something here, but don't write anything. I just want you to think about something. What we're saying is between 0 and pi over 4, we must be going up, but we must be concave down. So look at a concave down, right? This is what a concave down looks like. If I go to this peak point, when I'm to the left of this peak point, am I going up or am I going down over here? Up. To the right of the peak point, am I going up or down here? Down. The only way to go up a frown is if you're which side of it? The left side, right? So this information together with this information tells me that my function actually looks like the left side of that frown. Got it? Between 0 and pi over 4, my function must look like that. Yes or no? You got, I mean, this. Yes. Okay. How about between pi over 4 and 3 pi over 4? I must be going down the frown. So the right side of a frown. Between 3 pi over 4 and 5 pi over 4, I must be going down a smile. Which side of the smile is it? Left side. So I've got to look like the left side, right? Then from 5 pi over 4 to 7 pi over 4, I must be going up a smile, which means I must be the right side. And finally, to be going up a frown again, I've got to be which side? Left side. Understand? Okay. Now, I said leave space below that, right? Below this, I'm going to draw the function. And I'm going to use this information to draw the function. So I'm going to draw it like this. Here's my x-axis. Here's my x-axis. And then, let's see, my y-axis is over here, isn't it? Because that's x equals 0 over there. Over here is 2 pi. So I'm just going to translate these points straight down. Straight down. Straight down. Straight down. Now, I already got some information about these points, didn't I? I found the local maximum and minimum, didn't I? And that happened, what was it, at pi over 4 at a local max? And what was the value? You remember? Root 2 over 2. So let's say that, root 2 over 2, I'm sorry, not root 2 over 2, it was just root 2, right? Root 2? So I'm going to say right here I'm up at root 2. You agree that that point is on my graph? Okay, where was our local minimum? And it was where? Where did it happen? At 5 pi over 4? So if 5 pi over 4 had a local minimum, it was down here, right? And that was negative root 2? Y'all still with me? And then I had inflection points at 3 pi over 4 and 7 pi over 4. And when we plugged those into the function, we got what, zeros?
Yes.
We have a lot of the graph here, don't we? It might be worth it for us to just figure out what's happening at the two endpoints. Like what's happening at 0 and what's happening at 2 pi. So if I just take 0 and 2 pi and I plug them into the function, right, I could get 2 more points. So what is f of 0? What's f of 2 pi? F of 0, so you're going back to the original function, it's 1? F of 2 pi is also 1. Now where is 1? Root 2, is that bigger than 1, smaller than 1? Bigger than 1, right? It's 1.414 something. So 1 is like somewhere in here. And over here at 2 pi, it's the same thing. Got it? I think we have enough to draw this. So here I come with my drawing. Between this point and this point, I just need to connect these dots together, right? But because it's between 0 and pi over 4, it must look like this. So I'm going to connect these two with the left side of a frown. Like that. Okay, I should have stayed right there. Okay, like that. Then, from this point to this point, I'm between these two. It must be the right side of a frown. It's going to look like this. Okay? We all right? All right, between here and here, left side of a smile. So from this point to this point, left side of a smile. Then, here to here, right side of the smile. And then from here to here, left side of a frown. That's it.
So when you add cosine to the sine, it just phase shifts it by pi over 4?
Well, it also changed your amplitude, right? There was a lot of little subtle things happening in here. So let me take a look at this. How good was our graph here? Let's see. Sine, come on. Sine x plus cosine x. And let's lock our interval between 0 and 2 times pi. There it is. All right. Now, let me see if I can change something else here. So there, I changed my x-axis. Can you see that? I mean, that's exactly what we have, isn't it? I like ours better. So this is the idea here, and that's what today is about, is that we want to be able to use all the information to draw a picture. So what we're going to do is everything that we did last class is going to apply, but we're going to add some more stuff onto it. Okay, we're going to build a table at the end. We're going to use the table to graph. And then we're going to also, at the beginning, talk about some things that we didn't talk about here, like does our graph have X-intercepts? What's the left and right behavior of the graph? And this one, it was a closed interval, right? But like maybe in the future we won't close it, so that's where we're kind of headed. Yeah? Any other questions on the homework? No? All right, well, since there aren't any more questions, I'm going to move on to today's material. Which is curve sketching. And this is section 4.4. Now, there are lecture notes for this, as all the sections for this class, but I want to just show them to you because they're very short. Here it is. These are the notes for this section. It's just 9 steps, suggested steps for sketching a curve using calculus. All right? So what we're trying to do here is determine, figure out how you would figure out the behavior of a graph, the way it looks, a more precise picture of a graph than anything we've ever done before in our lives without a calculator, without a computer. Of course, we live in the day and age of the computer, but before the computer, this is the way it was done. What we're trying to learn, though, the most important thing for us, we're trying to understand how the derivative affects the shape of the graph and how important it is in determining, curvature and things like that. So what we're going to do when we start sketching is we're going to find the domain of the function, make sure we're very clear on what we can and cannot plug into the function. We're going to find any x and y intercepts if possible. It may turn out that they're too hard to find, so we just skip it. We check for symmetry. We look to see maybe it's an even function or an odd function so that we can maybe just get half of it and then reflect it over later or something. We find asymptotes. Now this can be a bit of a challenge. And then from steps 5 on is what we did with the previous example and then last class. So the first 4 steps are college algebra. The last steps are all the calculus steps. So let's start with this example. I want us to sketch f of x is equal to 2x squared over x squared minus 1. Now that's actually something that I would ask my college algebra class to sketch. We called it a rational function. We're going to do it, but with the additional calculus, all right? So y'all mind if I follow the steps? Is that okay with you? First step, I'm going to look at domain. So either tell me what I can plug in or tell me what I cannot plug in.
Plus or minus 1.
Plus or minus 1? Can't have them? Okay. X cannot be plus or minus 1. So that'll create division by 0. So I know that those points do not exist on my picture, right? All right, what about the x-intercepts and y-intercepts? So how do you find the x-intercepts for a function? You set it equal to 0, but because it's a fraction, you only have to set the top to 0, right? And that solution is 0, right? Now on this side here, I'm just going to, just so we have, this is not going to be my final picture. This is just so I'm thinking where I am right now. Right, I know I have an x-intercept at x equals 0. So I know that point belongs to my graph, right? Y-intercept. How do you find the y-intercept of a function? You plug 0 into the function, right? So plug 0 into the function. If we plug 0 in, we get 0, don't we? It's actually the same point as the x-intercept, isn't it? All right, so I've got that. How about symmetry? I'm not real big on symmetry, but are we going to have symmetry on this one? How could you check for symmetry? May I erase? Anyone need this? Okay. For symmetry, you could ask yourself this, is f of x equal to f of negative x? That means if I plug in, let's say I plug in, I can't plug 1 into that. Let's say I plug in 2 and I get some number, right? Is that the same as plugging in negative 2? And then if I plug in 3, I get this, and then over here, negative 3, do I get the same thing? If so, then wouldn't this, whatever this looks like, this would look like the same thing, reflected over? That would be symmetry. So is this true? Do I have this? is 2x squared over x squared minus 1 equal to 2 times negative x squared over negative x squared minus 1. They are the same, right? If I square negative, that's the same as this. If I square the negative, it's the same as this. So yes, this is actually symmetric, isn't it? This is symmetry over the y-axis. Now I'm just going to keep that in mind when I draw my picture, that it better look that way, right? Better look like a mirror image of itself over the y-axis. Fourth step, asymptotes. What were the types of asymptotes that we had from college? Vertical and horizontal. And slant, but we really didn't, depending on your college algebra, you may have spent some time on it. We're not going to look at them. We're not going to mess with them. Because we have the limit, we can figure out what's going on at the edges. So how about vertical asymptotes? Vertical asymptotes. Where do vertical asymptotes occur? Wherever the denominator is 0 and the top isn't. These happen when we get 0 on the bottom and the top is a number, right? Other than 0. What values of x cause that to happen here? Give me 0 down here without giving me 0 up here. Just 1 and negative 1, right? I mean, we kind of knew that when we started the problem. But we do have to be a little careful because sometimes we can have holes in our graph where it's the same factor on top and bottom, but that's not happening here. So I do have vertical asymptotes there. So let me come over to my graph. Here's 1, here's negative 1. I know that I have these dotted lines like this, right, that my graph cannot cross. How about horizontal asymptotes?
Degrees are the same for the equal exponent, so it's going to be 2 over 1, which is 2.
Yes, you probably recall that from college algebra again, that you can, if it's a polynomial rational function, which is polynomial divided by polynomial, you can look at the degrees and compare and all that. But this is calculus, and we have a different way of finding horizontal asymptotes. Horizontal asymptote tells us what the behavior of the function is at the edges, right? So instead of doing that, because what if this wasn't? What if this was like e to the x on top? Then we couldn't do that from college algebra. So what we use instead is this. We want to know what happens as x goes to infinity of this function, don't we? That's what we want to know?
Yeah.
That'll tell us what's going on out the right side. Yes?
So it's going to be x to, what happens to when x
Goes to infinity and negative infinity. We're going to look at both directions. Because if it's a rational function from college algebra, whatever happens out the left side happens out the right side. But that's if it's a rational function. If it's not a rational function, then you have to do a limit. L'Hopital, right? We got infinity over infinity? Yep, so let's do derivative of the top. 2, so limit, x goes to infinity. Forgot to put L'Hopital in here. 4x on top, what's on the bottom? 2x. X's cancel. You just get 2, which is the same answer you would have got using the college algebra technique. What happens as x goes to negative infinity? Does it change anything? No. Negative number squared, still, right? So using the same thing, L'Hopital, ... you get 2 again, right? So out both sides, it's headed towards 2. What's wrong?
Negative and positive because it's on the left and right side?
Left side and right side. The next example I do, you'll see that what happens out the left side will be different than what happens out the, happens out the right side will be different than the left, okay? All right, so again, going back to my picture, I know that at 2, at the edges, I've got these dotted lines, right, where my graph gets closer to it. Everything's college algebra, right? Well, no, that's a limit, so that's cal. So now step 5, determine where it's increasing, decreasing, and constant. So now we start bringing in the derivative. Yeah? Problem's going to take a while, right? These problems usually last about 40 minutes apiece. I didn't time us, but I'd say 30 minutes is a minimum for something like this. Started at 1:30? Okay, so I'm 10 minutes in, about a third of the way through the problem maybe. All right, so let's get some derivatives. So if I take derivative of that, I'm going to have to use quotient rule. And I better get it right, because everything else is going to be based on that derivative, right? So the derivative of this is going to be derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Ugh. Clean it up. Oh, that's nice. 2x cubed minus 2x minus 2x cubed over x squared minus 1 squared. Do you all agree with me? Yeah, I'm not. I was about to say I'm not feeling real good today. I've been on some meds and I'm like a little slow. So this is 4x, right? Derivative of top, 4x times the bottom minus derivative of the bottom times the top. So this should be 4x cubed and then minus, damn, I thought that was going to be nice. I guess not. See, I thought those x cubes were going to cancel. They're not going to. Wait, they are going to cancel, right? Look, this right here should be a what? 4. Okay. Go with me? 2 times 2 is still 4, Robert. All right. So they do cancel. All right. Negative 4x over x squared minus 1 squared. That's my derivative. We'll get back to that. I want to show you something real quick. I don't think I ever showed you this in this class, but I know that I have students that do stumble upon this sometimes. Is that the same thing as f? Is that f rewritten a different way? Just bringing the bottom up? Yes? If I ask you to take derivative there, could you do product rule? Yes? Okay, derivative of the first one, 4x, times the second one, plus the derivative of the second one is chain rule, right? So the negative 1 comes out, times x squared minus 1, reduce the power, negative 2, times derivative of what's inside, times the first function, right? You agree? That is, and if I rewrite this, this is 4x over x squared minus 1, bringing that down. This is minus these two together, 4x cubed, what's this, over what? Squared minus 1. And then if I put these two together with a common denominator, I would get back this, okay? I would. I'm just showing you there's more than one way to differentiate something. You can avoid quotient rule all the time if you're willing to. The give and the take is you can avoid quotient rule, turn it into product rule, but you're going to have to do a chain rule. Do you want me to put it together? Common denominator? All right, what do I get on the top right here? 4x cubed minus 4x, and then I'll have the same denominator, so minus 4x cubed all over the common denominator. This is this. I'm just showing you that, that's all. Not relevant to the problem? All right. I remember when I was a student in calculus, I think I stumbled upon that myself. I was like, you know, what if I brought that up? Could I still do it? And it worked out. I was like, wow, you could do that for anything. I mean, like you could rewrite it. It all works. That's good. It would suck if I did that and got a different answer than you did if you did it another way, right? All right, so there's our first derivative. Shall we get the second one while we're here? All right, second derivative. Second derivative is going to be quotient rule again. Yeah? Okay, derivative of the top. negative 4 times the bottom, x squared minus 1 squared. Minus the derivative of the bottom, which is going to require what? Chain rule. 2 times x squared minus 1 times 2x times negative 4x. So when we take derivative of the bottom, 2 comes out, that to the first power, derivative of what's inside of this, and then finishing off the product, the quotient rule, derivative of the top, not the derivative, all over what? X squared minus 1 squared, but then squared. So to the 4th? What a mess, huh? I think hopefully you can see why just putting one of these problems on a test would really test a lot of stuff, wouldn't it? 2, 4, 6, I believe I'm getting 16 x squared times x squared minus 1 over x squared minus 1 to the 4th. Do you agree with me or not? I didn't touch this. I put 2 times negative 4, which is negative 16. But then I'm subtracting that. So plus 16. I had x times x, which is x squared. Anybody see what we can do right now? Factor in x squared minus 1 out of both of these. Couldn't I? Could I not? And I'll cancel. So I'm going to pull out an x squared minus 1 out of the top, which leaves me with something up here. What's still up here? Negative 4, x squared minus 1, plus 16x squared. So after pulling one factor of x squared minus 1 out, that's what's left in there. And then that's all over x squared minus 1 to the 4th. Yeah? One more step. Let me clean up what's in the parentheses. Will you clean up what's in the parentheses? I'm going to write some stuff down over here. I know what you're thinking. You're thinking, where's my graphing calculator, right? Let me just graph this with my calculator instead. This is too much work. All right, so I'm just writing down the original function, the derivative, and then now I'm going to write the second derivative, just so we have it over here because I can refer to it. What does that numerator clean up to be here? 12x squared. 12x squared plus 4 over x squared minus 1 cubed. Boy, I hope we didn't mess anything up. I'm counting on you guys and gals.
Pull an x squared minus, no, never mind.
I could pull a 4 out. That's about as much as I could do there. I'm just going to leave
Yeah,
it.
it wouldn't,
Yeah.
it wouldn't work.
All right, so we got our two derivatives. We're ready? So we're trying to figure out where the function's going up and down. So I'm going to be working mostly, well, completely with the first derivative right now. So what I want to know is this. First of all, where is f prime equal to 0? And I also need to know where f prime is undefined. It is at 1 and negative 1, right? I'll get division by 0 here. So this is our first one that we actually have something interesting happening. So let's start with f prime being 0. What am I going to set equal to 0 for the derivative to be 0? Just the top. So negative 4x must equal 0, which means x is 0. All right. Something interesting is happening there. Where is f prime undefined? Whenever the bottom is 0, right? When x squared minus 1 is 0. What was that? Did y'all hear that? Is that like a high-pitched noise? Seriously? You did? Okay. Now, those points were not in our domain, were they? But there may be something interesting happening there. We might get some changing happening. So we are going to pay attention to it. Got a question? Go ahead. Yes, it is, but it doesn't matter because if this is 0, 0 squared is still 0. Yeah. Or if I wanted to do squared, the first thing I would do is take the square root of both sides. So
The square root of 0
it's still 0. Yeah. All right, so now I'm going to draw a number line, right? And I'm going to put these points on here. 0, 1, negative 1. Now, I'm going to actually do something here I haven't done, just to point out to you. Put a little red squiggly underneath those, the 1 and the negative 1. Why? Those are my asymptotes. Those, I do not have points on my graph there, do I? So remember that. But I'm still going to split my number line up and pick test points. So I'm going to have 1, 2, 3, 4 test points. Those test points will be plugged into the first derivative, right? So I need to figure out what f prime of, what test point do you want over there? Negative 2 here, negative a half here, half here, 2. Okay. Enjoy.
Only care if it's positive or negative.
That's all I care about is if it's positive. That's all you care about is if it's positive or negative, right? And there might be an easy way of figuring it out. I mean, in this case, it's going to be pretty simple because look at our derivative. The denominator is always what? Positive. So all I really care about is what's happening in the numerator. So what happens if I plug negative 2 in right here? I get positive. So this is going to be positive here. What if I plug in a negative number up here? Yeah, it's positive still? Yes? What if I plug in a positive number up here? Negative. And then negative again. So what this tells me is that over here my derivative is greater than 0, which means my original function is going up. Between here and here my derivative is greater than 0, which means my original function is going up. Here my derivative is negative, which means my original function is going down. Here my derivative is negative, which means my original function is going down. My test points were these, right? I'm going to circle my test points. These are my test, right? Test. Everything that's circled is tested. The critical numbers, the numbers that were important to us, that are part of our graph, that are going to give us our good picture, is the 1, 0, and the negative 1. Do I have local maximum?
Yes.
Yes? Where? At 0, because we have it going up and then down, right? Up and then down. Now, here's what you have to be careful with, is that if I say that I have a local max at 0, I better be able to plug 0 into the function. And can I? Yes, okay. So what I'm trying to get you to be careful with is what if we had done this, and what if this right here had turned out to be this? Would we have a local maximum at negative 1? A local max. You would not. Why? Even though you go up and then down, this point is undefined. Your derivative is undefined. To have a local maximum, right, this point has to be able to be plugged into the function. If it can't be plugged into the function, you can't possibly have a maximum there. Just ask yourself if that can get plugged into the function or not.
So yeah, if that happens, then you
No, you just know that you can't call it a local max.
Oh, okay.
That's all. That's it.
So you recommend drawing a graph in as you go along?
Well, what I recommend is that when you're trying to figure out where you have this change from up to down, that you just make sure that that point goes into the function before you call it a local max. If it doesn't, then it's just not a local max. An example of this is the function, and I think I showed you this before, the function f of x equals 1 over x squared. If you graph this function, it looks like this. And at 0, on the left side it's going up, right? On the right side it's going down. And so you might think, if you were to draw this table at 0, you would have got up and then you would have got down. So you would have said, oh, local max at 0. And where you would have caught yourself is when you try to figure out what that maximum was. You would try and plug 0 back in, you go, what? Right? So just be careful, that's all. So if you follow the process that I'm going through, it's hard to get tripped up because something's going to not make sense. But you still want to just be cautious of what you're doing here.
But here our value at x is 0, so that.
So we do have a local maximum here. We do. Mm-hmm.
And that value is 0.
And the value is 0, correct, for this particular problem. So I'm going to write that down now. I have a local max at x equals 0. And that means f of 0, when I plug it into the original function, was 0. So I know not only does this point exist on my graph, it should also be a local maximum, right? That point should be a local maximum. All right. Second derivative, right? Oh, yeah, oh, I forgot to ask about local minimum. We don't have any. What's that? Not applicable. You say it however you want. Say none. I don't care. But
So if they were to ask where f is increasing and decreasing, since it's not, it doesn't have brackets on it, it's not closed intervals.
you always use open intervals on increasing, decreasing. Just by default, always use open.
So it'd be like negative infinity to whatever.
Oh, yeah, no, okay, that's a great question. This is a really good question. If they ask you where it's increasing, what would you say? Because we don't have to do that for sketching. They're not asking us that. But where are you increasing? Negative infinity to, can't do it that. Can't do that.
Oh, negative infinity to negative.
Negative infinity to negative 1, union negative 1 to 0. Because you can't say that you're increasing at a point that is not in your domain. That's a good question. Everyone see that? This point's not in the domain, so f would be increasing from here to here, jump over that little asymptote, and then go from here to here. Decreasing, same thing. It would be from 0 to 1, union 1 to infinity. That's a good question. All right, concave up, down, that thing. So we're going to work with our second derivative. I want to know where my second derivative is 0. I want to know where my second derivative is undefined. We're 30 minutes in. All right, so what about this? Where is this 0? Well, I want to know where 12x squared plus 4 is 0, right? Where? That isn't happening, right? That's not happening? You're going to tell me that you're going to give me a number, I'm going to square it, I'm going to multiply by 12 and add 4, and then I'm going to somehow make that 0?